Now, let us talk about chapter 6, where we mainly talk about diversified topics as related to LTI systems. Consider a control system which has an impulse response of h of n. It takes an input of x of n and gives an output of y of n, in which case the output y of n can be expressed as convolution of x of n with h of n. Also, if Fourier transform of x of n is x of e power j omega, similarly, Fourier transform of h of n is h of e power j omega, and Fourier transform of y of n is y of e power j omega, then it can be written that y of e power j omega is equal to h of e power j omega multiplied by x of e power j omega. Similarly, if z transform of x of n is equal to x of z and z transform of h of n is equal to h of z and z transform of y of n is equal to y of z, then y of z can be written as h of z multiplied by x of z. From this we see that given x of n and h of n, to find y of n, one way is y of n can be found by convolution. Other way is transform x of n and h of n into either DTFT domain or Z domain and multiply them, then take inverse DTFT of inverse Z transform to get y of n. So from this we see that given x of n and h of n, y of n can be found out either by convolution or by the analysis in the frequency domain. From this we see that the plot of m is equal to apps of h of e power j omega with respect to omega is called amplitude response. It mainly gives an idea about the frequency content of the signal and can be used to characterize the system. Now, let us consider an example in which h of e power j omega is given as e power minus j omega minus a divided by 1 minus a into e power minus j omega. Here, the amplitude response m is the plot of apps of h of e power j omega with respect to omega. On simplification, that is, by substituting e power minus j omega as cos omega minus j sin omega in h of a power j omega to get apps of h of a power j omega, we see that m is equal to as shown. Upon taking the apps of numerator and denominator, we get m, and we see that in this particular case, this is equal to 1. So from this we see that the given system h of e power j omega here passes, sorry, the given system h of e power j omega has a magnitude of 1 for every omega. From this we see that the system is all pass system as it passes all the frequencies. Now let us consider another example in which h of e power j omega is given as 1 plus e power minus j omega. Here we see that m is equal to abs of h of e power j omega. Upon substituting e power minus j omega equal to cos omega minus j sin omega, we see that m is equal to square root of 1 plus cos omega plus sin omega whole square. This is equal to 2 cos square omega by 2 whole square plus 2 sin omega by 2 cos omega by 2 whole square. Upon simplification, we see that m is equal to 2 cos omega by 2. From this, we see that upon plotting h of e power j omega, abs of h of e power j omega with respect to omega, we see that the magnitude varies as 2 cos omega by 2, that is cosine in cosine form. So, if we try to plot the same, we see that at omega equal to pi by 2, the magnitude, at omega equal to pi, the magnitude is 0. Similarly, at omega equal to minus pi, the magnitude is 0. And at omega equal to 0, the magnitude is 1. And the magnitude m varies as cosine. From this, we see that the given system 1 plus e power minus j omega passes the low frequencies and it attenuates or blocks high frequencies. From this, we see that the given system acts as low pass filter as it passes the low frequencies and blocks the high frequencies. Similar to above, the plot of phi is equal to phase of h of e power j omega with respect to omega is called phase response. Similar to the magnitude response or amplitude response, phase response is also helpful to characterize the system. Now, let us consider an example in which the system h of e power j omega is given as e power minus j omega. This can be written as cos omega minus j sin omega. Here we see that phase of h of e power j omega is equal to minus tan inverse of tan inverse of imaginary part, that is minus sin omega, divided by real part, that is cos omega. Upon simplification, this is equal to minus omega. From this, we see that the phase of given h of e power j omega, that is e power minus j omega, varies in a linear fashion with respect to omega. From this, we see that the phase varies in a linear fashion, so the system is called linear phase system. Now, from the frequency response, we can get one more quantity that is called group delay, which is defined as minus d phi by d omega. The plot of g of omega with respect to omega is called group delay response. From this, we see that for a linear phase system, that is, the phi of omega is equal to a omega plus b form, the group delay g of omega can be written as minus d phi by d omega, that is equal to minus a. As a is a constant, we see that the group delay is constant. From this, we see that for a linear phase system, the group delay is constant. This can be proved for the system e power minus j omega given above. Now, let us look into another topic, that is filters. Filters are mainly helpful to extract useful information from the given input, and they are mainly classified as two types depending on the nature of the filter. The first cla- the first one is FIR filter. In this, the output at any instant n input depends on only input. So in this case, the impulse response is of finite length. For example, y of n is equal to x of n minus x of n minus 1 is a FIR filter. Here we see that the output at n depends on input at the instant n and n minus 1. Also, if you see for this LTI system, the impulse response h of n can be written as 1 comma minus 1, which is also of finite length. Now, let us look into another category of the filters, that is IIR filter. In this case, the output y of n at any instant depends on input as well as output. Also, in this case, impulse response will have infinite length. For example, y of n is equal to half multiplied by y of n minus 1 plus x of n is an IIR filter. In this case, we see that the output at any instant n depends on the output at other instant and the input. To find the impulse response of above filter, if we take Z transform on both sides and find h of z is equal to y of z divided by x of z, we get h of z as 1 minus half z inverse. If above system is causal, the ROC is mod z greater than half, as ROC should be outside a circle. So in this case, the impulse response can be written as h of n is equal to 1 by 2 whole power n u of n. So from this we see that in case of IR filter, the output y of n depends on the output at other instants and the input. Also we see that in this case, the length of the impulse response is infinite, in the sense that if h of n is plotted with respect to n, we see that h of n dies out as n tends to infinity. These are the two categories of the filters that we can discuss about. Now we will look into different types of LTI systems. Here we will mainly be looking into now let us look into some of the standard LTI systems. The first one we will be looking into is a minimum phase system. In case of a minimum phase system, the phase variation or the energy variation with respect to omega is minimum. Also, if the system is causal, in case of a minimum phase system, the poles and zeros are inside unit circle. So in this case, we can say that if poles and zeros are inside unit circle, the minimum phase system, that is say h of z, and the corresponding inverse system, hi of z, which we will be discussing about shortly, will be stable. So, for example, if you consider a causal LTI system which is of system function h of z is equal to 1 minus half z inverse divided by 1 minus 1 by 3 z inverse, we see that in this case the poles p is equal to 1 by 3 and zeros z is equal to 1 by 2 are inside the unit circle. So if the system is causal, then it implies that the system is minimum phase system as well. If you take another causal system, h of z is equal to 1 minus 2z inverse divided by 1 minus 1 by 4 z inverse. Here we see that the pole P is located at 1 by 4 and the 0 is located at 2. Here we see that as poles and zeros are not inside the unit circle, we can say that the system is not minimum phase system. Now let us look into another category of the LTI systems, that is linear phase system. In case of linear phase system, the plot of phase of h of e power j omega with respect to omega is linear. So from this we can say that phi of omega will be of the form a omega plus b, where a and b are constants. So from this we can say that the group delay of a linear phase system, that is minus d phi by d omega, will be equal to minus a. That is the group delay would be a constant. So we can say that in case of a linear phase system, the plot of phi of omega is linear and the group delay g of omega is constant. If we consider an example in which the phase of a LTI system is, sorry, the system function of a LTI system is given as h of e power j omega is equal to 1 plus j tan omega. From this, we see that phase of h of e power j omega is equal to tan inverse of tan omega, which is equal to omega. From this, we see that the plot of phi of omega with respect to omega is linear. Let us consider an example in which the system function h of e power j omega of a system is given as 1 plus j tan omega. The phase of the above system phi of omega is given as tan inverse of tan omega, which is equal to omega. From this we see that as phi of omega is linear with respect to omega, the given system is linear phase system. Also, if we find out g of omega, which is minus d phi by d omega, we see that it is constant for a linear phase system as discussed. Now let us consider another example in which it is given that h of e power j omega is equal to cos omega plus j sin omega by 2. If we find out the phase of the above system, we see that it is equal to tan inverse of sin omega by 2 divided by cos omega. If we try to plot the same for different omega, we see that this plot is not linear. So the system is not a linear phase system. Also, please note that there is a property of the linear phase system that we are going to talk about. Before that, suppose A is a complex number, then the pair A comma A star is called complex conjugate pair. Similarly, if A is a complex number, the pair A comma 1 by A star is called complex conjugate reciprocal pair. So in case of a linear phase system, If there is a 0 located at A, then we can say that definitely there exists another 0 at 1 by A star. This is the property of a linear phase system. If the system is linear phase and the impulse response is real, then if there is a 0 located at A, then definitely there are zeros located at 1 by A star, 1 by A, and A star. This is because there is a 0 located at A. As impulse response of the system is real, there is 0 should be complex conjugates. So there will be another 0 located at A star. Also, as the system is linear phase, 0 should be conjugate reciprocal pair. So A comma 1 by A star is a conjugate reciprocal pair, and 1 by A comma A star is another conjugate reciprocal pair. So from this we can say that the zeros of a linear phase system form conjugate reciprocal pairs. So for example, if we consider a LTI system which can be expressed as h of e power j omega is equal to 1 minus 2 into e power j pi by 3, sorry, h of z is equal to 1 minus 2 into e power j pi by 3 z inverse multiplied by 1 minus b z inverse. We see that in this case there is a 0 located at z is equal to e power j pi by 3. Also, if this system is linear phase, then we can say that there will be another 0 located at b is equal to 1 by z star, as zeros form conjugate reciprocal pairs. From this, b is equal to 1 by 2 e power minus j pi by 3. So, from the property that zeros of a linear phase system form conjugate reciprocal pair, we see that zeros are located at 2 into e power j pi by 3 and 1 by 2 into e power minus j pi by 3. Now, let us consider another case in which it is given that the system function of a linear phase LTI system is given as h of z, and the impulse response h of n of the LTI system is real. It is given thus a 0 of h of z is located at 3 into e power j pi by 4. Then we need to find the location of the other zeros, which are at z star, that is 3 into e power minus j pi by 4, and 1 by z star, that is 1 by 3 multiplied by e power j pi by 4, and 1 by z, which is equal to 1 by 3 into e power j pi by 4. So from this we see that by using the property that the given system is linear phase and has real impulse response, we see that the zeros are located at 3 into e power j pi by 4, 3 into e power minus j pi by 4, 1 by 3 into e power j pi by 4, and 1 by 3 into e power minus j pi by 4. Now let us look into a table. Sorry. Now let us look into some of the properties of FIR linear phase system. Suppose a linear phase LTI system has impulse response as h of n such that h of n is equal to minus 1 whole power n multiplied by h of n minus n. This is for 0 less than or equal to n less than or equal to n, sorry, minus 1 whole power p multiplied by h of n minus n. So it's given that there is a LTI system of impulse response h of n which satisfies the relation h of n is equal to minus 1 whole power p h of n minus capital N, where 0 is less than or equal to n is less than or equal to n, depending on the case that p is equal to 0 or 1, that is sign is positive or negative, and depending on the case that n is even or odd, We can classify the linear phase systems as type 1 or 2 or 3 or 4. So from this we see that given a linear phase system whose impulse response satisfies a condition, depending on the value of p, that is 0 or 1, and depending on the nature of n, that is even or odd, we can classify the linear phase system into four types as shown. So from above we see that if the linear phase system is of type 1, we see that n is even and p is equal to 0. If the system is of type 2, then we see that n is odd and p is equal to 0. If the system is of type 3, we see that n is even and p is equal to 1. That is, in this case, the negative sign appears. Similarly, if the system is type 4, then n is odd and p is equal to 1. So from this we see that based on the nature of n and p, we can classify the system as either type 1 or type 2 or type 3 or type 4. Now let us look into another category of LTI systems, that is all pass system. In case of a all pass system, the system function can be generalized as h of z is equal to z inverse minus a star divided by 1 minus az inverse. From this we see that in case of an all pass system, there is a 0 located at 1 by a star and there is a pole located at a. From this we see that in case of a all pass system, the poles and zeros form conjugate reciprocal pair. If the impulse response of the all pass system is real, then the system function can be written as h of z is equal to z inverse minus a star multiplied by z minus a, z inverse minus a divided by 1 minus a z inverse multiplied by 1 minus a star z inverse. Here we see that as the impulse response of the system is real, zeros are located at 1 by a star, 1 by a, and poles are located at a star and a. From this we see that if a 0 is known, we can find the pole of the alpha system. If the impulse response of the system is real, if a 0 is known, we can find the other 0 and the remaining poles in case of a alpha system. Also, upon substituting z is equal to e power j omega, we see that abs of h of e power j omega is constant. So that is, with respect to omega, the plot of abs of h of e power j omega is constant as shown in the figure. That is, it passes all the frequencies. Now, let us consider an example in which there is a system function given as h of z is equal to z inverse minus 2 phase 30 degrees divided by 1 minus b z inverse. If the system is all pass system, we need to find b. From the above, we see that the 0 is located at z is equal to 1 by 2 phase 30. So that implies the pole is located at p is equal to p, that is equal to 1 by z star, which would be equal to 2 phase minus 30 degrees. From this, we see that in case of a alpha system, poles and zeros form conjugate reciprocal pairs. So the value of B from this is equal to 2 phase minus 30 degrees. Now let us consider another example in which it is given that there is a alpha system whose impulse response is real. It is given that in case of this alpha system, there is a zero located at 2 phase pi by 4. We need to find the location of the other zeros and poles. So we know that in case of an alpha system, if the impulse response is real, we know there is a zero located at z star and there are poles located at 1 by z star and 1 by z. So from this we can see that the location of the other zero can be written as z2 is equal to 2 phase minus pi by 4 and the location of the poles is p1 is equal to 1 by z, that is equal to 1 by 2 minus pi by 4 and p2 is equal to 1 by z star, that is equal to 1 by 2 phase pi by 4. From this we see that depending on the system is all pass and depending on the nature of the impulse response, given the location of a zero or pole, we can find the location of other zeros and poles.